This is your fairly typical spectrometry setup using a diffraction grating here. A couple of power supplies. We've got our gas discharge lamp here. This particular one is helium. There's some other things you'll want as well, but let's go through them bit by bit. First of all, you'll need your gas discharge lamp. I've chosen helium because this is nice and bright. And you need a high potential, an EHT supply to drive it. So I'm using this one. The numbers are much of a nonsense because it broke, but it doesn't matter. I don't actually need to know what potential there is across this, just that it's high enough that this thing is glowing. The helium gas is glowing. Now what happens is the light passes into a slit. And we can make this slit narrower or we can make it wider. You see here I'm making it wider. If I turn this dial the other way, I can make the slit narrower. You want the slit as narrow as possible so that you get as crisp an image as possible, less uncertainty, but you want it wide enough that enough light gets through. And you can see in this room that I'm working, it's not exactly pitch black, so it's going to be quite wide for a slit. You position the slit so that it is lined up with the source of light. And you can tell when you've got it lined up by looking down this collimating telescope. And when you've got it just lined up, that's when it looks very bright, the image of that slit. Then what we want to do, making sure that everything is correctly positioned, and there's all sorts of dials to control that. This dial gives you fine control over that top platform, the angle the top platform is on. You want it to be so that the light is coming from the collimating telescope normal to the diffraction grating. There's a few ways you can check that. This here just tightens up this top platform so that it moves with the bottom one. Anyway, you take your diffraction grating. Now this diffraction grating is 300 lines per millimeter. You place it there, and you make more careful measurements than me to make sure that this light is going to be normal to that platform. Now when you look through the diffraction grating, we ought to see, let's just get this lined up first and I'll carry on the video. Right, let's try that again. You ought to see when you look down it, can you see there's an orange line in the middle? I'm ignoring all of the, get my pen out so I can point at what I'm looking at. I'm ignoring all the coloured lines at the top, because what's happening there is light from above, from there, is leaking through. Now what I could do to prevent those lines that are going across the top there, what I could do is place a piece of shield here, maybe a piece of card or something to block some of that light. But look, I know about it, so I can just choose to ignore it. So right in the centre, you can see there's a solitary, single, yellow-coloured line. Right in the centre. Let's get the tip of my pen out. Right there. But if I look to one side, you can see several lines. If I look even further to one side, several lines again. Trying to force the camera to focus on them. And let's say these are spaced out. Blue, yellow, red. Move around further, blue, yellow, red, even more spaced out. So this is the 0th order. That's what we call it. Right in the center there, that's the 0th order. There, get in focus. We've got the 1st order there. And then if I keep moving around, we've got the 2nd order there. So that center one contains all the colors that we can see. And then we see blue, yellow, red, then we see blue, yellow, red, and so on. So that's the setup. Now what we need to be able to do is measure the angle for each of those diffraction orders to determine the wavelength, and then using Planck's, Einstein's E equals hf, we can determine the excitation energy from this lamp that's given rise to that particular wavelength of light. And that's where this second telescope comes in. So this should rotate freely without dragging the platform around. You can see clearly that's not quite working as it should. So I need to fiddle with these dials I might just need lubricating, to be honest with you. Let's see if I can improve it. I wasn't able to improve it. Doesn't matter though, I've got it all lined up. So you put this collimating telescope, this collimating lens, here. So this is the, this over here would be the objective lens, and this over here would be the eyepiece lens. If we look through this, I'm not sure if I'm going to be able to get this focused. For the straight through beam, the 0th order, you should see a crosshair, and you should be able to line it up with that 0th order. Fine. So what we need to do is go find the second order, or the first order, then the second order. I'm going to use the second order because larger angles are going to give me less uncertainty on the angles. So let's go find that second order. I'm moving everything together. Nothing can go wrong. So as I move this over, moving it around slowly, bit by bit. Oh, what's that? That's a blue line. Next to it is a very lighter blue line, perhaps green. So that's the first order that we've seen. We carry on going around, there's that yellow line, carry on going around, there's that red line. Sorry, this is so wobbly. So that's the first order. We want the second order. First order's at this sort of angle here, so not a great angle. This was straight through, we've moved around by a few degrees. So let's go find the second order. Now here's the second order, the dark blue, perhaps I could even call it purple of the second order. It's very difficult to see, it's very faint. And that's with the slit as wide as it is. And that's because this room is so lit. If the room was black, and blacked out, I could make the slit much thinner. I'd have less uncertainty in the position of the various orders, but I could also see more faint orders, which I can't currently see. But it doesn't matter. There's the second order. If I carried on moving it around, I'd see the second order purple, blue, yellow, red, fine. Now, before I do anything, if I want to measure the angles, I actually have to measure a difference in angle. I have to know what angle the straight through is as measured off this angular vernier scale here, and then measure the angle for each different color. So I need to go put it back at the 0th order and measure that angle. Okay, that's the 0th order lined up again, as you can see. So I'm going to measure the angle. Just a little thing about this, if the image isn't quite in the right place, if it's too high or too low, you'll have to adjust these screws to move this telescope up and down, and these screws to move this telescope up and down, in order to get the beam to go straight through. Anyway, let's measure that angle. Now I'm going to use this scale here, because as I move this around, this is the eyepiece lens, I've just moved around the apparatus to make it easier. As I move this around, it's going to be harder and harder to get to this scale. Maybe, maybe not. I'm going to use this one anyway. I need a light source to help me with this. There it is. And I'm going to turn this on and off lots. So I need a nice source of light, and then you can see my scale's actually really horribly tarnished. I need to get some Brasso on it to clean it, so that's not easy to see. But it is in fact a vernier where we have 30 arc seconds on the vernier part, and then degrees and half degrees on the main scale. So 30 arc seconds is half a degree. So that's how this vernier works. You've got to be a bit clever with it. Now I actually have a lens as well to help me. It's only a flat lens, but that'll be fine. I've got a lens to help me read this angle. So if I move the lens like this, oops, other way around is clearer, then you can start to see that there's a V on the vernier one, and then 10, 20, 30. The vernier looks like it's just past 265 and a half. Looks like it's just past 265 and a half, so I'm going to make a good reading. Right, let's write down. I'm just going to write down that the 0th order was 265.5 degrees. I'm just going to go to the nearest 0.5 degree because it was really difficult to read that vernier without a proper lens. I could go over the road and get one, but I can't be bothered. I'm just showing how this works. So this is as accurate as we're going to get it. Right, let's move it back to that second order and start measuring some angles. That's the second order purple. So you can see I've got it lined up again with the purple line to just about make out. It's quite faint. So now we're going to measure the angle for the second order purple. And I'll write that down. It was 281 and 5 arc seconds. 281 and 5 arc seconds. So let's just put down here on my table, just like that. That's a non-standard way of writing it, but that's what 5 arc seconds are. Right, let's go get another color. So I'm going to move it again to another color. Okay, there's a greeny blue color at this angle. I've moved it, and if I look through, you can see the greeny blue color there. So this is still the second order. And I could call this sort of green blue-ish. Let's go find that angle. So if you get the angle of the light and the lens just right, it becomes much easier to read. You don't have to move things around a bit. Oh, that's quite easy for me. I don't know if the camera's picking this up. 281 to 282 and a half, and it was nearly 283. So yeah, it lines up on the 28th. So that's 58. So 282 and 58 arc minutes. 282 and 58 arc minutes. In the standard way of writing arc minutes, by the way, is you'd write something like 282 seconds and then 58 arc minutes. And then there are arc seconds as well, which are a 60th of an arc minute. Oops, you can't see what I'm doing. So that's the normal way of writing things down. But degrees, what a plonker. 282 degrees and 58 arc minutes. And then if you add any arc seconds, they'd go there. That's the normal way of writing your angles. I've written them like this because I already put degrees up here. So if I hadn't put degrees up there, I'd have written them properly. But there we go. Doesn't matter. It's going to be easier to use them like this anyway. Let's go find another color. Right, at this angle, I get the 0th order like an orangey yellow, and it's a really bright one. So the dominant color right there. So that's a second order orangey yellow. I can't write. Orange. It's probably close enough. Right, let's go get the angle. Okay, so that one was 285 and 58 60ths. All right, let's go find the next one. Right, now it's too dim for me to see the next one. I know there should be a red in there somewhere, but I can't see it. So what I could do is I could go find the first order red, and I could record it like this and so on. Anyway, once you've got the data, what we're going to do is use this equation. N lambda, where n is the order, lambda is the wavelength we want to calculate, equals d sine theta, where theta is the angle of diffraction, but careful, it's the difference between these two. Okay? So each of these subtract that to get the diffraction angle. So perhaps I should call this theta prime or something, and it's theta I want to put in here. With d, we know that there were 300 lines per millimeter, so it's going to be 1 over 300 lines per millimeter. Now we're probably going to want d in meters, and that's the same as 10 to the negative 3 over 300 meters per line in terms of units. So we can bung that in a calculator if we can't do it ourselves to get d. It's not too tricky. So what I'm going to do is calculate lambda for each of these. I'll do that now. So now with these data, I calculate the actual diffraction angle I want to use, which is just that subtract that is that subtract that is that, and so on. Then I use my value of D, which I've calculated here, in this equation here. So D, which is that, times the sine of each of these angles, divided by n, which in all of these cases is 2, gives me lambda, the wavelengths. And I've done those calculations there. So 448 nanometers, 500 nanometers, 583 nanometers, they all sound reasonable. Then we use this equation, E equals hc over lambda, to determine the energy in joules, and then divide that by E, where E is the elementary charge unit, 1.602 times 10 to the negative 19, just like that, and that's going to be in coulombs, divided by that, and that will give me my energy in electron volts, and there they are. 4.44 electron volts, 2.48 electron volts, 2.13 electron volts. Now what I could do is I can look these up in a big book of elements, a big book of stuff, and see whether they are the excitation energies. You can get loads of different excitation energies, and you can get excitation energies for the same colors but for different orders and then compare them. Then you've got uncertainties because you've got a range of values for each of those excitation energies. So you've got uncertainties then as well. And people cleverer than me produced a list of excitation energies and figured out from that what the energy levels had to be, given that each excitation energy is an amount of energy difference between two energy levels. That's quite an accomplishment. And maybe you could do that yourself if you want, but there we go. That's how to use a spectrometer.